Hey everybody, today's section is going to be on polynomial and rational inequalities. Now what this section pretty much amounts to is either given the graph and some particular inequality, represent the answer in interval notation, or as we'll see later on in the section, it will give us a polynomial or rational function. We will use a method very similar to the last section to solve for the intervals that satisfy the inequality, also called solving the inequality. So let's start off here with the graph-based problems. And so for this first problem, you'll notice in the class notes that these diagrams are given. And so we're going to start off with, well, the problem wants us to determine when is the function less than 0. So when we're given a graph, what this is saying is ultimately what parts or what interval or intervals of the graph are underneath the x-axis. That's another way of what this is asking for. And you can look at the graph and identify the parts that are in fact below the x-axis. There's this loop right here, or this hump right here, and there's this segment over here as well. So that's two different segments that are below the x-axis in this problem. And we need to find a way to represent them. And you might notice in the statement of the problem, it says, put the answers in interval notation. So we're going to start off with this hump right here that I referenced earlier. So remember, with graphs, when we're identifying intervals, we use the x values, and we're going to put this in interval notation, so please be familiar with that process, but it's left to right ultimately. And so the furthest left we go, they give us the number. It's -1. And for now, I'm just going to write -1. I'll worry about the bracket parentheses stuff in a bit. So -1 is the furthest to the left here. In fact, let me give that a bit of space, as you'll see later. So -1, and then the furthest to the right we go seems to be this particular point right here, which is 0. And to determine the brackets and parentheses, well, what you have to notice here is that they're forcing us to use parentheses. Notice we do not have an equal to component. So we don't have an equal to component, that's why we're going to use parentheses here on both sides, just simply because the problem is stated to not include the ends. But we're not done yet, because we did identify this segment here, but there's still this segment down here, and we need to denote it using a very similar idea. Now, something we've noticed in, say, previous sections, maybe the one before last, is using the union, or maybe in the beginning of the chapter, using the union whenever we had domain problems in interval notation. In this particular problem here, the main keyword is that they do not tell us to separate answers with a comma. In fact, what they want, they call it the solution set. And what the solution set is, well, it's singular, which means they want one thing. The solution set means all the intervals that satisfy, say, representing the graph being below the x-axis, have to be glued together. This is a singular thing because of the way they're asking for the problem. So that's what motivates a union symbol here. So remember the union, it means the glue between intervals. So right here, this represents this segment over here to the left, and now we're going to add something on the right over here. So it's this segment in particular. The furthest to the left this segment goes is 2. And we'll again worry about the parentheses and brackets in a second, but that 2 corresponds to the furthest to the left we can go. The furthest to the right, you may notice we hit an arrow. So that means we go to the right, positive infinity. And of course, the infinities always get parentheses, and 2 will also get a parenthesis by the same logic as before. This one gets a parenthesis simply because we do not include the endpoints. This might be different in this problem, as we'll go ahead and see now. So this ultimately says, well, let's flip the logic. Let's look for when the graph is above or equal to the x-axis. So we just flip the way we're looking at this. This segment right here is above the x-axis, so let's go ahead and start with it. Again, this is left to right. What's the furthest to the left we can go? We hit an arrow, which means negative infinity. It's negative infinity here. So if anything, negative infinity. And of course, the infinities always get parentheses. The furthest to the right we can go is -1. And we ask ourselves, does -1 get a bracket or a parenthesis? And in this part, for part B here, it's going to get a bracket because we're including the endpoints. We're including when the function hits the x-axis. So -1 here gets a bracket for simply that idea. But you may notice this segment is not the only segment that's above the x-axis. There's also this segment right here that is also above the x-axis. So let's go ahead and prepare by putting a union, remember the glue between intervals, and now we need to notate this segment. So this segment starts at 0. And we're going to use a bracket because we are including the endpoints here. So 0 is the starting point of this segment, and the ending point of this segment, if we just trace it, we hit +2, which also gets a bracket. And so that would conclude this first problem, these two answers respectively, and we'll go ahead and move on to example 2 over here. So with this problem here, it's very similar in terms of setup. So something to keep in mind, this is a section on polynomial and rational inequalities, which means you're going to see polynomials and you're going to see rational functions. So polynomial graphs are the ones that are continuous, no asymptotes, nothing like that. Rational functions, well, the opposite. Rational functions generally have asymptotes scattered about. They're normally discontinuous. And so that's something to keep in mind. And we'll see more examples throughout the section. So over here, it wants to know when this rational function is above the x-axis or greater than 0. And so we're going to use the same idea as before. We just need to be careful, just in case. So when the function is greater than 0, let's identify all the places where this is greater than 0. This segment right here, that definitely seems to be above the x-axis. So we need to represent that using an interval. Well, interval notation. So what's the furthest to the left that this graph goes? We hit an arrow that goes to the left, which means negative infinity. Okay, so negative infinity is how we start. The furthest to the right this graph goes, well, you might notice something. That's what makes rational functions and inequalities a little bit trickier than the polynomial counterparts. So here, the furthest to the right, we start to converge with this dotted barrier, the asymptote here. So we try to go to the right as much as we can, and this is a barrier that we can never touch. Remember, asymptotes, in particular vertical asymptotes, cannot be crossed. So the way we notate this is, well, we can't touch this barrier, but let's go ahead and represent it anyways, because it gives us an idea as to how the graph will end off, what the tail end does. And so that tells us that the rightmost we can go for this segment is -3. So -3. And we're going to use a parenthesis because we are not hitting the asymptote. I mean, additionally, it restricts us regardless, but we have 2 reasons why we would not use a bracket. And this will make more sense, I think, in part B. So just hang with me. And so we're going to use a union. And the reason why we're using a union is because this is not the only segment that is above the x-axis. This segment is also above the x-axis, but just this segment. So notice it starts here. So we're not going to include the whole thing. We're only going to include the half that is above the x-axis. And so that segment, the furthest to the left we go, is right here. That's where it starts at the x-axis and continues to go upwards. So that's at 0. So that's at 0, and we're going to use a parenthesis simply by how the problem is stated. And then we want to see how far to the right we can go. Well, the furthest to the right, it's the same logic as for this part. We keep trying to go to the right, but then we realize that there is an asymptote in the way. There's this barrier. And this barrier, well, the graph never touches it, but it does give us some intuition as to how the tail end of the graph behaves. So we will use the asymptote as part of our answer. This asymptote corresponds to 2, to x equals 2, and that will be the other end. And a good rule of thumb, asymptotes will never have brackets. Well, at least vertical asymptotes. Vertical asymptotes will not have brackets. We'll see this, you might notice in the notes, we have a few more graph-based problems, but that's a good rule of thumb. And so this would be the answer for part A. And then part B, well, it flips the inequality sign and it adds an equal to component. So let's look for all the places where the function is, well, below or equal to the x-axis, or when the y values are less than or equal to 0. So we can go ahead and just simply identify them first and then notate them second. When we look at the graph, what we notice is this segment that stops at the origin will be our first segment that we write down, that we notate. So everything from this arrow all the way to this point, that's the first segment that is less than or equal to 0, or equivalently below the x-axis. So what's the furthest to the left we can go? The furthest to the left, we start to converge with the asymptote again, which means we want to use the asymptote as an indication of our leftmost behavior. So the leftmost behavior, the graph gets really, really close to -3, but doesn't quite touch it. But we could still use that asymptote as an idea of the behavior. And we're going to use a parenthesis, even though the problem has an equal to part, that part is thrown out the window when asymptotes are involved. I mean, they're asymptotes for a reason. They are not something that the graph can be represented by, but it is something that helps us identify behavior, general behavior. So we're using a parenthesis because the -3 was an asymptote. That's the rule of thumb here. And then that's the leftmost behavior. As we go to the right, we hit the origin. So we stop here because we want under the x-axis only. So we stop here, and so that x value is 0. And since 0 is not an asymptote, that is why we're going to use a bracket here, because it does say provide any endpoints, and, well, don't throw in any asymptotes. And so this would be the answer. However, we have another segment that is below the x-axis, so we have to get all of them. So that's when we're yet again going to use the union. And with the union, now we want to represent this interval, this segment right here. So we start off with the leftmost behavior. It goes to the left all the way to what looks like x is equal to 2. And we're going to use a parenthesis, mainly because this is an asymptote. Doesn't matter if it has an equal to part. Asymptotes do not get equality. So that's the leftmost behavior. In the rightmost behavior, we hit an arrow to the right, which means positive infinity, which always gets a parenthesis. And this would be our answer to part B. And that would conclude this problem. So So now we'll move on to, well, two problems that are very similar to the previous two. We have a polynomial graph and a rational function graph. So let's go ahead and start with the polynomial function. And so for this problem, all it wants us to do is solve for one inequality instead of two. And you may notice I didn't write the function down that came with the problem, and that's because they give us the graph as well, which really simplifies the process that we're going to do in order to solve the inequality. So this inequality in particular wants us to determine when the function is less than or equal to 0, or in other words, when is the function below the x-axis or equal to the x-axis. So that's what we're going to look for. And when you look at the graph, you may notice, all right, it starts on the far left underneath the x-axis, and so as we trace it to see how far we can go, we do hit a point that is on the x-axis. However, we don't have to break this up at all. Our inequality has the equal to part, which says we can continue to keep going, even if we do hit the x-axis. So we don't have to break this interval up at all. If that equal to sign was gone, then we would have to break this interval up. But since this equal to sign is there, we can keep going, which means we are still underneath the x-axis, and we hit 4 here, which then transitions to being above the x-axis. So starting from the left here, all the way to 4 right here, that's what is all less than or equal to the x-axis. We do not have to break up here, because the equal to allows us to keep going. And so how do we denote that interval there? The furthest to the left we go, we hit an arrow, which to the left, that corresponds to negative infinity. And to the right, again, remember, we do not have to break up here. It's because we can equal the x-axis, and everything to the left and right is still underneath the x-axis, so we can keep going. And so where this actually stops at is at 4, at positive 4. So we have 4, and we want to include 4, so I'm going to use a bracket because we want to include where the graph hits 0 for that endpoint. Notice this value here, -1, it's not an endpoint. We can keep going on the right-hand side. So this actually would be your answer. So this is a type of problem that, well, the answer is simplistic, but they throw this tricky intermediate step in the way to try to throw you off. So just be careful of that. And there will be a problem without the equal to part, where you will have to break up this inequality accordingly. So I'll let you try to figure that one out. But we will move on to problem 2 here, which is, well, the same idea, but now we have a rational function. And this wants us to determine when the rational function is, well, again, less than or equal to the x-axis. So here's the x-axis. We notice that this segment starting from here all the way to this point right here, this is the only segment on this whole entire graph that is below or equal to the x-axis. So that segmentation is now what we need to denote. So this segment right here, this is the only segment on the whole graph that is below the x-axis. So the furthest to the left we go, so we play the same game. The furthest to the left we can go, we hit this arrow because, well, it doesn't mean we're going to the left forever, because notice there's a barrier right next to it, which means the barrier prevents this arrow from going to the left forever. So for the, I think in example 1, the second problem, we had something very similar to this. Asymptotes exclude any sort of equality, no matter what, but they do give us an idea of how to represent the behavior. So although this graph never will equal this asymptote, we could still utilize the asymptote as a way to denote the leftmost value that our graph can go. So from the left, that value would be -2. And it always has parentheses, no matter what. Asymptotes do not get brackets. So instead they get parentheses, just like how infinity always gets parentheses. Asymptote, same idea. So that's the furthest to the left, we utilize the asymptote. The furthest to the right, we keep going, and this point that I drew in, that is the furthest right that we can go while still being less than or equal to the x-axis. And we need to figure out the x value of that point. Well, it's between -2 and 0, so -1. And this -1 value, it's not an asymptote, and it does want us to include the endpoints as long as it's not an asymptote, so we will use a bracket. And this right here will represent our answer for example 2, part 2. And that would conclude this problem. So now we move on to solving inequalities algebraically without having the assistance of a graph. And so really the remainder of this homework set divides between solving polynomial inequalities algebraically and rational inequalities algebraically. And you'll notice that they work out very similarly. But let's go ahead and start with this one. And so the first thing, something I mentioned earlier actually was that the process for this was something we actually used in the previous section. So if you understood that process or you need more work with that process, I'm going to detail it here once again. But I'm going to reword it slightly as you'll see momentarily. So the first step here is going to be factor completely, put it in a factored form. So put in factored form. This is just a general first step. You may notice it's already in factored form, so we don't have to worry about this step, but say for the next problem that we're going to look at, this will be more relevant. So for now, we can skip that. Move on to step 2, which is, well, a step that we're familiar with, as I mentioned from the last section. It's list all, and so we're going to list all the zeros and the domain restrictions. And the domain restrictions. Again, this is something that we did in the previous section. In this problem, we don't have to worry about any domain restrictions because there's no denominator. So we don't have to worry about it here. So all we're looking at are the zeros, which are the opposite numbers for each factor. That's why factoring is nice. So for this first factor, the 0 that we get from it is +3. And the other factor, or the other factor, the 0 that we get from that is -5. So that's step 2 right there. Just list all the zeros and the domain restrictions, if any. And so 3, plot on a number line. So we'll go ahead and do that. So we're going to plot all of these numbers on a number line in order. So here's our number line. We'll go ahead and start with the smallest number first and move on to the larger number. If we had more numbers, we would just append them on here as needed. And so this is where that idea of test points comes into play. So remember, test points, this is when the number line, so the whole number line has now been split into 3 different sections. This section, and this section. So from each one of those sections, we're going to determine a test point. Each one of these sections will derive a different test point. The only criteria is that this test point has to come from the corresponding interval that we're pulling it from. And notice I'm using a different notation here. This is to distinguish these from the numbers I listed up here. So the criteria of this one, it just has to be less than -5, so I'll pick -6. And then from here, it just has to be between -5 and 3, I'll pick 0. and has to be larger than 3 for the last one, I'll pick 4. And I did notice in the last section, there's 2 ways of doing this type of problem actually. And in the previous video, I explained both ways. In this lecture, I'm also going to explain both ways. And I'll start off with this method here. The next problem, I'll explain it the other way of doing it. So we get the 3 test points, and remember for this method of working out this problem, it's a matter of plugging each one of these into the original function and seeing whether we get a positive output or a negative output. So it's a lot of just plugging in numbers and seeing what happens. So we'll go ahead and do that. So we'll start off with, let's do x is equal to -6. So whenever we plug in x is -6 into the original function, that just simply replaces every x with -6. So -6 minus 3, quantity squared, and -6 plus 5. And so what that comes out to be, well, I happen to see that it's going to be a positive number from here times a negative number, and a positive times a negative is a negative. Feel free to just plug in all the numbers and get your output whichever way you want to, but yeah, so all we care about is the sign. We care about whether it's positive or negative. And here we get a negative number. The number itself doesn't matter, it's just the sign of the number. So when we plug in -6 for x, which came from here, that means that the corresponding sign is negative. And as a result, we get the sign and we scratch out the test point. This is exactly what we did in the previous section. We're doing it again. So now we move on to 0 when x is 0. So we have x is 0, it's the same idea. 0 minus 3 squared, 0 plus 5. This comes out to be a positive. 0 minus 3 quantity squared is always positive, and 0 plus 5 is a positive number. Oops, just a positive. Which means we get a positive output. Again, you can plug all of this in your calculator if you want to, or you can break it up factor by factor like I did here. You get a positive number from here, a positive from here, a positive times a positive is a positive. It's up to you. But we do get a positive number, which means when we plugged in 0 for x, we got a positive number as our output, which means a positive would go up here, and we can now scratch out the 0. And now we move on to the last one, 4. When x is 4, what happens? So let's look at that situation. When x is 4, it's, well, same idea. 4 minus 3 squared times 4 plus 5, and that's definitely going to be a positive number. 4 minus 3 is positive 1, squared is 1, 4 plus 5 is positive, everything's positive. All of this is alluding towards is that when we plug in 4 for x, we get a positive output for y, and that means we can scratch out our test point of 4. So finally, you might notice, so the problem that I got this from, it's organized a little bit differently. In fact, in particular, they have a table that you have to fill out first before you put the final answer. And the table doesn't really affect things too much outside of the natural steps here. So the table is just having us add one more additional thing. So I'm going to make room for this table that I'm mentioning here. So I think this resembles most closely example 9 from the homework, problem 9 from the homework. And you will notice that they do have a table. And let me make sure I represent the table appropriately. So the table is in the format of interval, sign, and then they give 3 separate columns here, where each column is going to involve the interval itself and whether we get a positive or a negative. So in other words, they want us to, there's going to be blanks in each one of these cells in the table. And so the interval is referring to, well, how to represent this interval using interval notation. Same with this one, same with this one. So what we're doing here is we're going to represent this interval first. Again, this is a good reason why we canceled out the test point. We don't want to use the test point to determine the interval. So this interval seems to be negative infinity to negative 5. And that's exactly what goes here. Negative infinity, negative 5. And I'm going to use parentheses here because we had strictly less than. So again, that's negative infinity to negative 5. And now it wants to know the sign of that interval. Well, the sign of that interval is negative. So negative, I think it'll be a drop-down option, and you just simply select negative. For the next interval, well, the next interval is this one here, from negative 5 to positive 3. So we'll go ahead and put exactly that down. And again, we're using parentheses simply because they are excluding the equality to the ends. So that's the next interval, and that interval is positive. So you would put positive here. And so finally, well, the last interval. The furthest to the left is positive 3. Furthest to the right is positive infinity. So we go ahead and write that. Again, everything has parentheses because we do not have an equality part. And so the interval that this represents, well, the sign of this is positive. So again, we put positive up here. And this would answer the tabulated part of the problem. And then it goes on to ask for solving the inequality, which, if you notice, solving the inequality, so notice we found negatives and positives. Which one do we pick? We pick the negative one. This is less than 0. So what numbers are less than 0? Negative numbers. So that's why we're going to look up here and simply pick all the intervals that have negative corresponding to them. There's only one. So we only have to put down the one answer. So this is the, I guess we can call that part A. And then part B, the final answer would be negative infinity, comma, negative 5. Because this corresponds to, this is the only interval that corresponds to a negative output for that interval. And we want negative because this is less than 0. If it were greater than 0, we would have picked the positive columns. And we'll see this more as we go through these problems for the remainder of the homework section. But this would conclude this problem. So we'll continue to look at problems of this idea, solving inequalities algebraically, and we'll do another polynomial-based problem. So we're going to start off by utilizing the factored form, by putting this in factored form. So you may notice, well, not only is it not in factored form, but everything is, it's not even in standard form. So normally standard form, one of the requirements that we've been given for free is putting everything on the same side of the inequality symbol. So to even begin with this, what we need to start off with is by subtracting the 25x squared on both sides, so ultimately moving this over to the left-hand side, so we can get this into standard form. And the sign still remains greater than. So if anything, We didn't factor, but we put it in standard form because standard form is helpful whenever we factor. So you will notice that for a few problems throughout this section, it may not be in standard form and you have to first put it into standard form. But now that you have it in this form, you may notice that these two terms, they have something in common. They both have an x squared in common, which means you could factor out x squared. So x squared, and once you factor out x squared, x to the fourth now becomes, well, x squared. And then minus 25x squared, well, we just took out the x squared, so it's now minus 25. And now this is greater than 0. And so from here, we're not done. This can factor more. X squared minus 25, you should be familiar with this. This is a difference of two squares. So what this is x plus 5, x minus 5. It's a difference of two squares. X plus 5 and x minus 5. And this would be the fully factored form right here. This is everything fully factored. So I'll go ahead and write that over here because that's what we want to look at for now on. So it's the same exact problem. It's just written in a very convenient way to where we can extract a lot more information about the problem than beforehand. So now that we have the factored form, so one of the helpful things about this form is we can figure out the zeros really easily. Because remember, we have to list all the zeros and the domain restrictions. So list all zeros and domain restrictions, as we did in the last problem. Well, we're not going to have any domain restrictions, just like in the last problem. We don't even have a denominator, so we can scratch that. Zeros, though, we have 3 zeros from this problem. Remember, the zeros, we get 1 0 from every factor. X squared is a factor. This is a factor. It's the same thing as x plus 0 squared. So we do get a 0 from this. That 0 being, well, 0. So 0 comes from x squared. Negative 5 comes from the next one. And positive 5 comes from the following one. So these are our 3 zeros. And from here, step 3, as we did before, step 3 is plotting them on a number line. And again, we'll plot them in order. Negative 5 on the left, 0 in the middle, 5 on the right. So, as I mentioned for the previous example, there's 2 ways of working this out, this next part out. The previous part, I worked it out one way where we plug in every test point from every segment. In this problem, I'm going to work it out the other way. So you can use this to maybe pause the video and try it an initial way if you'd like. So from here, this second method, it's somewhat similar, but what we're going to do is utilize multiplicities. We'll get to that in a second though. The first thing you have to do with this method though, that I'm going to explain, is you need to pick a number that is larger than all the numbers you found over here in step 2. What's a number that's larger than 0, negative 5, and positive 5? Well, let's pick 6. So, here, we're going to pick 6. There's a reason why we're doing this. I'll mention that in a bit. So we're going to pick 6 and plug that into the original function. And plug into function. So what we do now, we're plugging in 6 into the new function that we got over here. So not x squared, but that's going to be, well, 6 squared. times 6 plus 5 times 6 minus 5. And we're not going to worry about the inequality. We're plugging it into the function for now. We'll come back to the inequality. So here, you get a positive number, and a positive number. All we care about is the sign of the output. So here we get a positive number, and so that tells us that so we picked 6. We picked the number 6, it was the largest. And because it was the largest, that means it comes from this segment over here. So 6, of course, it's larger than 5. So what we did was we found just that sign. We found that this was a positive value. So over here, this is a positive value. And if you want, you can scratch out the test point here. So so far the methodologies are the same. What distinguishes the two is we don't have to choose test points from the other segments. We can use the multiplicity to determine the adjacent signs. So the multiplicity, so to get from this segment to this segment, we have to go around 5. To go around 5, we need to know the multiplicity of 5. So if we go back to our factored form over here, we can see all the multiplicities here, here, and here. And I'll go ahead and write these understood ones just as a reminder to us. Don't keep these ones in my math lab, by the way, they won't accept it. So the positive 5 here has a multiplicity of 1. I'm going to write m as 1. M just means multiplicity. And why is m 1? The factor that positive 5 comes from is this factor right here. Because remember, it's the opposite. What's the exponent? It's 1. That's it. And remember, and this is an odd exponent. So even more important, it's an odd multiplicity, which means crosses. So that means this sign, whenever we go from this segment to this segment, that sign has to alternate. What is it crossing? It's crossing the x-axis. What happens when you cross the x-axis? You go from positive to negative or negative to positive. So that's why we're going to get negative right there. Because whenever we dance around or jump around 5, which has an odd multiplicity, you have to change the sign. So now we look at 0. And 0, what kind of multiplicity does 0 have? 0 came from x squared, which means its multiplicity is 2. So I'm going to put m is equal to 2. And that's an even multiplicity. So what that corresponds to is, if ever you plug in, or if you cross around, let me not use that terminology. If you go from this segment to this segment around 0, an even exponent, normally that means touches, but what that generalizes to is that we do not have to alternate the signs. In fact, we don't alternate the signs. Negative will stay negative. So notice I am putting a negative. These have to agree. That's what an even multiplicity corresponds to if you use this method. And then finally, to go from this segment to the final segment, what we need to do is figure out the multiplicity of negative 5. Negative 5 comes from this factor with an exponent of 1. So that tells us that the multiplicity is 1. This is odd. And so that means if ever we dance around the negative 5, we have to flip the sign because that's crossing. So this would be positive. And so we did all of that work to construct this number line, but we're not done because the problem initially asked, well, solve the inequality, but this number line will definitely help us. We only have one more step. We can go ahead and append that down here. So again, notice when we had the factored form, we don't care about the initial form anymore. The factored form gives us much more information here. And even in particular, it tells us that we want the values that correspond to greater than 0. What numbers are greater than 0? Positive numbers. So here we want the final answer, we want the positive intervals. So because this is greater than 0, we want the positive segments. And so we need to figure out this segment here in interval notation and this segment over here in interval notation, because those are the ones that have the plus signs. This segment over here, this goes from negative infinity to negative 5. So negative infinity to negative 5, and I'm going to use parentheses throughout because we don't have an equal to part. That's why I'm using parentheses. If we did have an equal to part, I would consider brackets. And since we have another segment, I'm going to use a union here to attach or glue together disjoint intervals. And so this is the other segment that has a positive sign. It starts at 5 and it ends at positive infinity. And this right here would be our final answer. So this second method is definitely a lot more helpful when you have a problem that has a lot of zeros or domain restrictions, virtually when you have a lot of numbers right here. And I'll do both methods again for the next two problems, but for now that would conclude this problem. So we'll move on to solving rational functions algebraically instead of polynomial functions, which means now we have domain restrictions to factor in. And so for a problem like this, so the preliminary steps are still going to be the same. We'll start off with, well, it's already in its factored form. So one, if you start to consider the factored form, it's already good. It's already in the factored form. So I think the majority of the rational function ones, I think there's only one where you have to factor it accordingly. But after that, so we're already in factored form, that's good. So now we can list the zeros and the domain restrictions. So far, we've only had zeros to worry about, but now we're going to also consider domain restrictions. And so the zeros still correspond to the factors from the numerator, as similar to the polynomial problems we just looked at. So we get positive 2 from this one right here, negative 2 from this one, and domain restrictions is simply a way of referring to the zeros from the denominator. So the zeros from the denominator, well, we just get x, but x is a factor. You could think about x as x plus 0, but in other words, we get 0. So these are different types of numbers. These two are actual zeros, and 0 itself is a domain restriction. This will come into play a little bit later. And so step 3, this is where that number line comes into play. We'll go ahead and generate the number line and plot all of the listed numbers in order. So, as I mentioned, there's 2 different ways we can proceed for this problem. I'm going to do it via picking a test point from every region. In the next problem, I'll do it the other way of just picking one test point and using the multiplicities. So from here, the number line has been split into 4 different regions, and we're going to pick a test point from each one of those regions or segments. So this segment, and so on and so forth. And so we ask ourselves, okay, what's a number that's less than -2? Well, we could pick -3. A number in between -2 and 0, -1. A number in between 0 and 2, +1. A number greater than 2, 3. So we have 4 test points, so let's go ahead and, for this method, plug in each one of those and determine the output, the sign of the output. So go ahead and do that now. So when x is -3, so remember, we're plugging that into the factored form. So now -3 gets plugged into every x value. So now it's -3 minus 2 times -3 plus 2 divided by -3. And from here, so you could throw all of this in the calculator. If you were to do that, I'd recommend putting in the numerator, then putting in the denominator, and then dividing at the end. Or you can use the sign, compare the signs. -3 times -2 is a negative, -3 plus 2 is a negative, divided by a negative number, that's a positive, and then we will get a negative in total. So that tells us for the segment corresponding to -3 for x, we get a negative number. So we put a negative sign here, and the test point is gone. Okay, so for x is equal to -1, we go ahead and plug in -1 into every x. So -1 minus 2, -1 plus 2, divided by -1. And so what we get is a negative, a positive, divided by a negative, which is a positive number. And so I already have the positive here. So if you're wondering why I cut abruptly, I kind of messed up at this portion of the video, but yeah, so that positive would correspond to a positive for -1, that x value that we plugged in, and we can go ahead and scratch out the corresponding test point. And so for the other two values, it's the same idea. I'll just go ahead and put what their signs will be, a negative and a positive. You're more than welcome to test this out to make sure everything matches up. But from here, so this will be one of those problems like we did, not the last problem, but the previous one, where we'll have a box and you have to put all the information in a specific way. So what I'm going to do is simulate that just to give you all an idea of how to answer that. So the box in particular, but yeah, we can go ahead and scratch out these as well. So the box in particular is, it'll have interval and sign and a bunch of columns for each segment. So the first segment will refer to this one right here, coming from infinity to -2. And you will represent it exactly as such. If you're wondering why -2 has a parenthesis when we have an equality here, that's just the preference of my math lab for now. This equal to part will come into play later, but we'll save that, of course, for later. So this was the first segment, and then the next segment, it's -2 to 0. And we keep going. Next one is 0 to 2. And the final one is 2 to positive infinity. So for this portion, they just want all of the endpoints to have parentheses. And that's just my math lab being picky. And so for each one of those intervals, it wants to know the corresponding sign. We get negative, positive, so that tells us exactly what to put. Negative, positive, negative, positive. So that would answer the first part of this problem. And the second part, it wants to know what the solution set is. What will actually solve the inequality over here? So notice this inequality, what it tells us is that it wants negative values because we have a less than sign, but it also has an equal to component. So that's going to bring something new that we haven't been exposed to yet. In particular, what it will do is it will make all of these zeros have brackets on them. Not the domain restrictions, but all of the zeros. So remember, we found 2 zeros here. These were the zeros. Remember, those are the ones that come from the numerator. So anytime we have an occurrence of this number, or either of these two numbers in our final answer, they have to have brackets to correspond to the equal to part. So we want all the negative columns. We have 2 of them right here. So here's one, here's one. So let's go ahead and start jotting those down. For this column, the interval is negative infinity to negative 2. And that's where this chart gets a little bit misleading, because if you didn't notice that, you would just put down this interval, union this interval, and think you're done, and then wonder why it's telling you you're incorrect. But this equal to part tells you that any zeros have to have a bracket on them. Negative 2 is a 0, so it has to have a bracket to correspond to the equal to part here. And then union, because we have another segment, 0 does not get a bracket. Notice I'm putting a parenthesis next to 0, but a bracket next to 2. So why am I doing this? It's because 0 came from the denominator portion. And that means it's a domain restriction. Domain restrictions never get a bracket. That's why 0 is not getting a bracket. But 2 is not a domain restriction. It's just a 0, and that's okay. So that's why this one has a bracket, and this would be the final conclusion for this problem. So we're going to look at probably the most hardcore of the rational inequality-based problems, mainly because of the amount of factors that we have, which means our listing, when we get to it, will be pretty large. And we'll use the other method that I was talking about to figure out the particular intervals that satisfy the inequality. So we'll start off with the factored form. So you might notice everything's factored. There is one slight thing I'd like to change for this setup, and that is, so they present this factor as 7 plus x. That factor is technically not in standard form, and what I want to do right fast, so I'm not even going to write it down over here, I'm just going to change 7 plus x simply to x plus 7. And this might help with any possible confusion later on. So all I did was just switch the order of the terms just to put it in standard form. So with that, this would be factored form. So we have 1, 2, 3, 4, 5 factors, which means we will derive 5 various numbers in terms of domain restrictions and zeros. So I'm going to list the zeros first. Remember, those are the numbers that come from the factors in the numerator. This one right here, so x squared is a factor. It's the factor corresponding to 0. So 0 is one of them. Negative 7 is another one, and positive 9 is a third one. And if you want to, you could definitely make a note that these are zeros, and this might come into play later. In fact, this will come into play later, so we'll go ahead and make a note of that. And in addition to that, so that was the zeros, now we need the domain restrictions. The domain restrictions are the ones that come from the denominator. So we get -2 and +7. So -2 and +7. And those are the domain restrictions. And I'll just put DM, domain restrictions. And so we'll move on to part 3, which is, of course, the number line. And now we have 5 numbers to plot, and we have to put them in order, which just means -7 goes first, and then -2, and then we have 0, and 7, and then 9. So we have quite a few here. And from all of these, we're going to go ahead and pick test points. Well, all right, let me back up. We're not using that method for this problem. The method we're using, we have to pick a number that is larger than all of the numbers that we listed here. So what's a number that's larger than all of these? 10. The largest number is 9, we'll pick 10, which does come from this segment. So we're always, I would suggest you always pick one number from the far rightmost segment, which is, in other words, pick the number that is the largest or larger than all of these. And so the 10 is now going to be what we plug into the original expression over there and see what the sign of the output is going to be. So if we plug in x is equal to 10, we plug that into every x, so now it's 10 squared, and 10 plus 7, 10 minus 9, all of that divided by 10 plus 2 and 10 minus 7. If you throw all of this in your calculator, again, I would suggest putting the whole numerator in first, then the whole denominator in, and then dividing at the end. Or you can use the signs, the comparison of the signs, which would be a positive from 10 squared, a positive from 10 plus 7, a positive from 10 minus 9. We get a bunch of positives ultimately, which will give us a positive value. And with that positive value, that tells us that the segment that 10 came from is a positive segment. And now we can get rid of that test point. And so now we can fill in the signs of the other segments by using the multiplicity idea. So to go from this segment to this segment, we have to dance around the 9 here. So the multiplicity of 9, that 9 came from this factor right here, and it has an exponent of 1. And in fact, we can go ahead and do this for all of these right quick. -7, it seems like all of them have a multiplicity of 1 except x squared here, which means that all of these have a multiplicity of 1 except for 0, which came from x squared. It has a multiplicity of 2. So 4 out of 5 of these are going to have a crossing behavior, while the other one is even, which means it will touch, and we'll see what that means in a second. So it's organized just like this. And now, if you can represent all this information in a clear way that makes sense, then I would definitely recommend this method, because we don't have to plug in any other numbers. It's simply a matter of what's the multiplicity of 9? It's an odd number, which means the sign will change. It has to alternate, which means we go to a negative. And then to go from this segment to this segment, we have to dance around the 7. What's the multiplicity of 7? It's an odd number, which means we have to alternate again. So notice negative becomes positive. For 0 here, 0 has an even multiplicity, so it's different. So an even multiplicity says that the sign, it stays ultimately. And then crossing around -2, that's a minus. And then around -7, that's going to be a plus. So they only alternate whenever the multiplicity is odd. They do not alternate, such as this example here, when the multiplicity is even. But ultimately, this is the construction we have now. And you could have also picked a test point. You could have picked 8 and +1, -1, -3, and -8. You could have picked test points from all of those and you would have gotten the same answer. So let's go ahead and throw all of this together. So now the question is, we have positives and we have negatives. So yeah, the question here is, well, which one do we want, positives or negatives? And that comes from the very beginning. This is greater than or equal to 0. Greater than 0 implies that we want the positive ones. So we want this segment, that one, and that one. So let's go ahead and write out all the positive segments. But also remember that some of these, so remember the zeros, because there's an equal to component here, any zeros that we list are going to have a bracket. The domain restrictions, I just noticed that I put DM. I have no idea why there's an M there. Okay, let's try that again. Domain restrictions. Okay, sorry. So now that we have the number line filled out, we can go ahead and, well, solve the inequality. So in particular, what are we looking for here? Are we looking for positive intervals or negative intervals? And it turns out, simply by virtue of the greater than sign, greater than 0, we are looking for positive intervals. The equal to part, that comes into play by including all the zeros. So any 0, because of this equal to sign, is now included. The 0 here, the -7 over here, and the +9 over here. So now all of these are included, and the domain restrictions have open circles. You never include domain restrictions. So we can go ahead and denote the final answer as all of the positive intervals, where we use brackets at any zeros and parentheses at any, well, what end up being vertical asymptotes or domain restrictions. So we can go ahead and start off with this segment because it's positive. This segment starts at -infinity and it ends at -7. And we include -7 because we filled in the point there, so that's why -7 would get a bracket. We're going to use a union because now there's this segment that is also included. But something to keep in mind though, so to actually notice this segment and this segment, they're both positive and the number splitting them up is included. So it turns out that if you were to list these two from -2 to 0 and then from 0 to 7, this would be a redundancy because the number for which we're splitting up is also included. So we don't really need to split it up. So yeah, kind of confusing point, I know, but what that ultimately amounts to is that we can combine these two intervals together into one interval because we no longer need to split up here. So what that looks like, so now this whole interval is combined into one, and so we have -2 on the left, so -2 on the left here. We can skip past 0 because we combine these two segments together, and we go all the way to +7. And then finally, we can go ahead and add the final positive interval, which is 9 with a bracket, because we do have 9 filled in, all the way to +infinity. And this would be our final answer. Finally, I wanted to talk about one of these, so there's going to be two domain problems at the end of the homework set, and although it seems to be, I guess, not in relation to the other stuff, the polynomial and rational inequalities, it definitely is for one mere fact of, well, how do we determine the domain of a square root function algebraically? So remember, the rule is the domain of the square roots of anything. So here x to the fourth minus 16. So this was on that list of domain criteria and steps, I think on page 21 or 22 of the notes. But this was, you set the radicand, or everything underneath the square root, greater than or equal to 0, and solve for x. That was the rule for square roots. And now notice, it reverts completely down to a standard problem from this section, which we'll go ahead and talk about because I think this helps out with another problem on your homework as well. So it's the same idea though. It's put it in factored form, which we do need to do in this problem. So the factored form here. So this one's a little bit unorthodox because, well, we haven't seen, there's no common stuff to factor out. This is one of those weird difference of 2 squared problems, which is why I want to demonstrate it, just to make sure everyone's on board. So here, the difference of 2 squares is coming from the fact that this term is x squared quantity squared. I know it's kind of weird, but it reduces down to x squared plus 4, x squared minus 4. And so that's technically the square root of x to the fourth, and then the square root of the 16. That's coming into play. So again, that's not something that naturally comes up in this class, but it does come up for this problem. But we're not done yet, because over here we have a difference of 2 squares. Over here, this does not factor. We do not have a sum of 2 squared formulas. So this, although it looks promising, will not factor. I promise, it does not factor. This one's a difference though, which means that one does factor. And so we can go ahead and finally write this down. So again, the plus version does not factor. The minus version is a difference of 2 squares, and so that's x plus 2, x minus 2. And so that is the form that we're going to look at. So I'm going to write it over here to the left, just as a reminder. And from here, we can go ahead and determine or list the zeros and the domain restrictions. So the zeros, if you try to find a 0 from here, you're going to be unsuccessful because you'll end up taking the square root of a negative number. If you're not interested in seeing this, you can skip over this part, but the reason why, if you try to find a 0 from this segment, then if you subtract 4 on both sides, you would get x squared equals negative 4, and when you take the square root, that's when you run into a problem. The square root of a negative does not work. So that is ultimately why you get no zeros from that factor. But we do get zeros from these two factors. We get negative 2 and positive 2. And from here, we can go ahead and put them on the number line. Here we have negative 2 and positive 2. And so from here, we can go ahead and use either method. I figure there's only 3 segments, so I'll go ahead and just pick 3 test points right quick. So negative 3, 0, and 3. and we plug each one of those into the function we have over here and see what the signs are. So we plug in -3. So that would be -3 quantity squared plus 4, -3 plus 2, -3 minus 2. And so this will give us a positive number, a negative number, and another negative number, which will give us a positive. So all of that to figure out that the sign corresponding to -3 is positive. And from here, we can scratch out the test point. And so if you plug in 0, you're going to get a negative. So for time's sake, I'll just go ahead and put in negative and positive. Again, you can use the idea of multiplicities and see that the multiplicities are 1 and 1 each. So now that we have that, we can go ahead and represent our final answer. So remember, the inequality that we dealt with, that tells us that we want the positive values. Notice there's an equal to part, which also means we include any zeros. So these are both zeros. So from here, our final answer would be corresponding to all of the positive segments. So let's start with this segment because it does have a plus sign. It's from -infinity, and it goes all the way to -2. And since -2 is a 0, and we have an equal to part, we put a bracket here. But we have to use a union because there's another part that's positive. It starts at 2, and it ends at positive infinity. And again, the 2 gets a bracket because it is a 0, and the inequality inherently starts off with an equal to component. And this would conclude our answer with this domain problem.